Hello, machine learning students. There are 2 of you so far. Now 19. $27 viewers. We had 130 last night, so hoping for a few more than 31 viewers. So I should be tweeting and such, and I better make sure that it's announced over in the machine learning channel. If anybody wants to hop over there and do that, I will take advantage of your free labor. And we got to go to the tweet space. And let's see, we're up to 39 viewers. I'll say this a couple of times as we progress through, I suppose. Still accepting applications for the machine learning course. So if you haven't applied yet, be sure to sign up. I'm pasting into the chat room for YouTube because I think everyone that we have in our Slack rooms already signed up. Go to this URL and click apply, enter your info, and we'll get you in for either the full-time or part-time class, which begins in about 2.5 weeks now. 47 viewers after 1 minute. We're doing all right. I'm going to give it about 2 minutes more, and then I'll get started. Okay, well, seems like a good time to get started. Get all my windows situated. Welcome back, Lambda School machine learning students. Today's the 3rd day of the mini boot camp. The first couple of days of the mini boot camp, I just talked about what machine learning is and how to do it, what tools are popular, what languages do you need, and a bunch of philosophical highfalutin about how to do machine learning. I haven't talked about why you should do it or what it's good for. I continue to leave that up to the 10,000 websites that are advertising the popularity of machine learning every day to tell you why to get involved. Please come and join us at Lambda School for our 6-month-long full-time class that's 45 hours a week, like a business, like a job, 8 to 5 Pacific time, or join us for the part-time class, which is 12 full months, Monday, Tuesday, Wednesday, and Thursday from 6 to 9 p.m. Pacific time, and also Saturday from 9 to 12. That's 9 a.m. to 12 p.m. It's got a little bit less material in it than the full-time course, but is available for a much larger number of participants. You know, once again, Lambda School's model is we invest in you. you don't pay anything until you graduate. Make it all the way through the course, graduate, get a job in machine learning or some related field, and you pay us a percentage of your income that maxes out to $30,000 over 2 years. So it's a pretty easy bet. You've already got the job by the time you're paying. Tonight's lecture's fun. We haven't gotten into the nitty-gritty yet of much, and tonight we're going to talk about mathematics. We're going to talk about the most basic element of mathematics, the one that makes modern mathematics possible by and large, the foundation of calculus. It's the next thing that comes after pre-algebra, if you will, and then everything else gets built up on top of it, and it's the most basic requirement of doing machine learning. However, you don't have to be a mathematician in order to do machine learning, and it's really, really, really hard to become a mathematician in 6 months. So if you haven't gone down that route yet, unless you're planning on spending 4 hours a night working on it, let's just stick to the machine learning course, and hopefully you'll learn enough to be successful. Tonight's about functions, y equals f of x. And there's not much point in talking about functions without drawing visualizations of it. So I'm just going to kick into screen share, and we will continue to discuss the almost second most basic operation in mathematics, the function f of x. All right, screen share coming your way. Part of the time with this lecture tonight, I am going to do handwritten equation drawing, which is a classic essential of mathematics. And part of the time tonight, I'm going to do equation generation using machine learning tools, NumPy, Python, and what have you. Let's see here. That link is broken. I just clicked it. Like I gave it to you from people in chat are saying the link that I shared to Lambda School is broken. Just brought it up again. I just copied it. I'm going to paste it in. I got to keep this headquarters up. Looks like the same one, huh? What's going wrong with it? When I click on the link, it doesn't work. I paste the link, it does work. I have to do some investigating on that one. Now's not the time. Must resist. Let me try pasting it in with an HTTP instead of an HTTPS. Someone posted a fixed link in Slack. Thank you. But that's the link that I posted. What's different about it? Does it have like a control character in it that I can't see? I pasted it in again. Click it. Page not found. All right, well then click back to our site. And then, gosh, that's weird though. Click on majors and choose machine learning emphasis. I don't know why the link doesn't work. I will debug it before the next session, but now it's not the best time for, we're going to debug functions right now. We're not going to debug web pages. Okay, back to functions. Okay, the function, the humble function. Let me switch to pencil. I have terrible handwriting. I have tried to do better, but it's still bad. School. Right. The humble function. All right. I'm not going to do any polling because this is just the mini boot camp. We're going to fly through it and we'll see what happens. Now, traditionally, what we do inside of Lambda School's course is I'd send a poll on Slack and I'd say something like, you know, who knows what a function is? Who's comfortable with it? And who is this something new to them? We're not going to do that tonight. We're just going to roll with the punches. So the function is most commonly written like this: y equals f of x. So you say of with the parentheses, just like in a programming language. F is the name of the function. And then x is the number that goes into the function. Just like in programming, this is the input. And this here, y, is called the output. Now, this can be rewritten in infinite ways. A function can be written without writing y equals f of x. But the most common way of writing it, or the simplest or the newbiest way of writing it, is to write y equals f of x. So any of you who have taken calculus, you have seen y equals f of x. Any of you who have not taken calculus, you might not have seen y equals f of x, or you might have just barely seen it at the end of your algebra classes when you learn something called y equals mx plus b. All right, and that's the function for a line. It's usually the first function that anybody learns when they're studying late algebra. And it's just the exact same thing as y equals f of x, except that we would say that f of x is equal to mx plus b. So we could say that here. But let's not get ahead of ourselves, because I want to give you an even lower level definition of what a function is, or even of what a number is, before we continue on piling on ideas on top of each other. Okay, and I should probably make these much bigger. I'm just going to close this and try a big one. Why not? How's visibility? How's the legibility in my handwriting? Gosh, how big should this be? 1700 by 1200. That'd be pretty much just about exactly perfectly right. All right, so but before we get into functions, we just need numbers, because a function is a pair of numbers. It's a relationship of numbers. And first we want to just talk about basic numbers to get us into the function. Okay, so you've all seen this before, odds are. And even if you haven't, it's pretty intuitive. It's a very famous thing to learn. Students learn it in probably 5th grade, called the number line. And a number line, essentially every number line is infinite. And it goes from 0 in the middle to minus infinity on the left-hand side and positive infinity on the right-hand side. Okay? But people will draw sub-images of it. It's easy to do something like this and just say, let's draw a number line that goes from 2 until 5. And all the other numbers are located there too, right? 3, oh, that's well drawn. 3, 4. And we can draw an unlimited number of these. And the basic approach to building a function in mathematics starts with this number line. And so what we do is we draw an axis that we call x. And it's kind of the number line. We say x. Okay? And we can put 0 on it if we want to, but we don't have to. Put a 0 here. And then x is that input that we saw before, right? F of x. F of x equals y. Okay, now y becomes a new thing that we'll get to in a minute. First, let's say x equals 0. What that means is when x is equal to this, y is some other number. So we'll go comma. Y equals what? Okay, but x can have any other value, and this is essential to the understanding of a function. X isn't just 0. X could be 1, or it could be, where does that go? Right here. Oh, come on. Lost the ability to, there we go, 1. X could be 1.414, which is a really cute number called the square root of 2, which would be right about here. Square root of 2. Or it can be 10. Draw that over here, 10. It can be -5, and etc. Okay? Now, the point of this is that each line along X we could call a sample. It's one particular place where we have a measurement. We input X for f of X at each of these values, and there is a Y value that comes out of them. And here's where things get interesting. Here's where functions start to get entertaining. Because when you draw a function, or when you graph a function, or when you write a machine learning model to understand a function, you get 2 axes. You get the first dimension X, and you get the second dimension Y. Okay? And the simplest function that we can describe here for f of X equals Y, or more traditionally, Y equals f of X, is for f of X to equal X. Okay? So this is the identity function. And there's more frequent times that you will see identity. So let's just write it out here. I, or identity. And it means the same thing as went in. Identity function equals the same thing that went in. So what's the identity function of all these values? Well, if X is 1, then Y is 1, right there. If X is the square root of 2, then Y is the square root of 2. If X is 10, Y is 10 here. See, and let's draw the little hash here. There it is, 10. Okay, so X10, Y10. And finally down here, X is -5, and Y is -5. And this is one more way that we can notate a function. It's exactly the same thing as writing Y of equals f of X. And we're going to see it in data all the time, but we can just write them out as tuples. We can say 1, comma 1, and also square root of 2, comma square root of 2, and also 10, comma 10, and also -5, -5. Okay, these are all f of X for this particular function. But we can change f of X anytime. And in fact, we will change f of X all the time. In fact, if you've done algebra, which hopefully you should have, because it's hard to capture this much math really fast if you haven't at least spent a few years doing algebra, f of X is really just a variable. It's really just a representative of some function. F of X really never means f of X. It means something else that we're about to talk about. Now, the last thing I want to draw a picture of before we move on with f of X to the next stage is that it's a requirement for a function, a numerical function of the kind that we talk about, that it be continuous and smooth. And what that means is that there is a value for f of X not just at -5, not just at 1, or at square root of 2, or at 10, but there's a value for f of X everywhere. Every single number has a value for f of X. And it creates a line. So if you plot every input of X into f of X, you get a line that grows across the page. Now functions start to become beautiful. So there's an even simpler function than the identity function. We could say that f of X equals 2. Okay, and that's just plain boring. That means for every single value of X, the output of the function is 2. So here's our number lines. Remember, there's an axis, X and Y. And no matter what we put in here for X across the X-axis, the output is Y. That's called a constant function. And they occur more frequently than you think. So it's good to know about. It simply means that the output of f of X is a fixed value no matter what you put into it. And you can also write it in a vector form, like we're starting to get into. You can say 0, 2, and you can say 1, 2, and square root of 2, 2, or 10, 2, or minus 5, 2. And they don't have to be in a specific order when we write them this way. We can write them out like this. This is called a 5 by 2 matrix, or we can write them out one at a time. 0, 2, 1, 2, square root of 2, 2. And so I'm showing you all these different representations because math is just visualizing numbers and manipulating them in your head. And there's all this really kind of crushing intellectual vanity wrapped up in the expression of functions and arithmetic and performing algebra on them, such that if you don't have the background, you think it's some kind of dark wizardry. But what I'm trying to present to you is that all 4 of these drawings, oh, that was different. Guess it's a little bit higher than it needs to be. Will it scroll for me? Come on, baby. Nope. All right, all these drawings are equivalent. They're the same thing. They mean the same idea, and they convey the same information. So f of x equals 2 is the shortest form way of writing this graph for every single number, or writing this matrix for every single number, or writing them all out in tuples. F of x is just a shorthand way of saying that anything you put in for x is equal to 2. Let me slow down for a minute because I'm on a roll. I want to make sure I'm covering all my details. I am covering all my details. That's sweet. Okay, so let's make things a little bit more interesting because we've only covered 2 ideas right now. A constant function oh, so hard to write, it's just slow. All right, and what's that? It is f of x equals c. And then what you would write, if you are a mathematician, is where c is a number. And you could say it was a real number or an integer. It's up to you what you want to say there. You can use more sophisticated notation to write this out, which you can learn about in a textbook, and you might see it. You might see something like this. F of x equals c such that c is in the reals. Okay, once again, really scary, complicated notation that means f of x equals c where c is a number. Okay, and this happens again and again and again and again in mathematics. If you haven't been doing it for 15 years, you go, what in the hell is that supposed to be communicating? It's actually quite simple. It's just been obfuscated by the academic industry that is piled on top of it. All right, let me check my chats because y'all know how I like to talk about stuff without reading it. All right, everybody's listening. Cool. All right, it is clearly just listening time. All right, we did the constant function. We also talked briefly about the identity function. All right, and the identity function, f of x equals x. All right, boring. All right, so functions get much more sophisticated. And my goal with this part of the talk, if I can do it quickly enough, is to show you cool examples of functions and their shapes up to a fairly complicated shape of a function called a Gaussian. And then we'll move on to the next subject of this talk, which is called the derivative of a function. And I better hurry up because the derivative takes a little bit of talking. All right, so aside from these 2 basic function names, there are not as many general classifiers, but there are an infinite number of functions. All right, the next one that we should cover, f of x equals 1/2 of x. Okay, and this one's a cool one to draw a graph of because this 1/2 is called the slope, which you've learned about if you finished algebra. We draw our 2 axes, x and y. And instead of going perfectly straight up along with x like that, it goes up at a flatter gradient. It's still perfectly linear, as was said in chat. Venkashwarlu, I'm not sure that you can join the Slack channel without having signed up for the course. Did you get the link there? I'm typing it in now. Maybe that link will work. Okay. And then this slope can be anything. It could be 3x. So we draw our x-axis. We draw our y-axis. And then instead of being linear at exactly the identity function, or instead of being slower than x, it's faster than x. It goes up really fast. Zip. Like that. Okay. These are all linear functions. Okay, functions don't get interesting until we add something called polynomials to them. Once again, if you have done late algebra, you should know what a polynomial is. This one is perhaps the most common one that is known, a quadratic polynomial, or x squared. Okay, and it makes the best, one of the very best graphs, because x squared is always positive, because a number times itself is always positive. A negative times a negative is a positive, and a positive times a positive is a positive. So what happens is, here's the y-axis. Here's position 0, 0. Here's the x-axis. And what you get is a curve. And that's actually going through 0, 0. And then it goes back up, and it's exactly mirrored around the y-axis. Okay, what is it? Well, let's pull some Python down here real quick, because when you see a number like that, you think, now I'm maybe now I'm feeling confused again. All right, so let's def f of x, and let's return x to the power 2. All right, now let's do this. This is a Python trick. We got to import some NumPy. And then we're going to make some values of x. We're going to get linspace. Linspace is one of the easiest ways of inputting this. We say x equals np.linspace from -3, let's do 3 to 3, and we want to have 40 samples in there. So now look at x. Sploot, it's a whole bunch of inputs. Remember, it's a whole bunch of x values along the x-axis here, from -3 to 3. There's 40 of them. Tick, 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 tick. And now we can do another thing. We can get y. Y is equal to, we have to do a cool trick with this. Vectorize f of x. All right, so now we've got x and we've got y. I lot. So plt.plot x and y. Now it's going to draw 2 lines. No, it isn't. Sweet. So look what I just drew. Zoop. All right. It's smooth and beautiful, and it's the essence of mathematics and the essence of calculus right here. But this curve, we can only see it because we know what the function is, okay? And I'm throwing this out here because in machine learning, you don't know what the function is. That's what machine learning is for. And so what you get is you get something a little bit different. You get this, plt.plot x sub 3, y sub 3. And you get plt.points, I think it's points, x sub 7, y sub 7. Point. Dot. Is it dots? Forget. I'm Googling it. We plot one single data point. Maybe I just try plot again. So what I'm doing is I'm plotting 3 separate values. And they're not visible. Font size bigger request? Yeah, I will. But I'm going to move away from the terminal again for a short time. I'll show you what I typed in though. It did not plot what I wanted, but I'll draw it here. What you see in machine learning is a dot here, and a dot here, and a dot here. And the purpose of machine learning, now remember we talked yesterday that the data is very high dimensional, okay? So you can't even draw this picture very easily. But you've got lots and lots of points in lots and lots of dimensions. And the purpose of machine learning is to build a machine that can intuit this shape from this dot and this dot and this dot. It does not know the shape of the data. It has to figure it out. $6.30. Okay, so this y equals f of x handles all the other graphs that you can draw, more or less. Y equals f of x. We can do x cubed. We can do sine of x. Now, sine is another special function. Sine's really cool, and I might as well explain it for you now since I have you. Yeah, find my plot. plt.plot. Let's do x to the third. plt.show. And look, here's x cubed. It's got another beautiful little curve to it. Whoop, nice. Let's do this one. We got to import math. Math.sign of x, so it needs to be vectorized. plt.show. Cool. Okay, the sine function, the famous wave function. Now, what is this wave function? It's actually a circle. I just want to tell you this because it's fun to share these anecdotes. It's a circle, a perfect circle, with a triangle inside. And the triangle has this angle measurement inside. Some people call it phi, some people call it theta. But the point of this sine wave that goes like this is that it is the length of the hypotenuse h as this triangle circles around the interior of the circle. So the triangle grows, for example, until it's really, really big, like that, and even all the way over to here where it crosses 0. And then it swings back down this way and all the way back to here. And the sine function is just the length of that hypotenuse as it circles around a circle. So when you see a sine function, what you're actually studying is the equation of a circle and its relationship to some other math every time you see it. Same thing as a cosine, etc. All right. There was one more that I wanted to show you before we move on to derivatives, because you see a lot of stuff in mathematics and computer science that's hard, that's really scary looking. And mathematicians never hesitate to drop the most frightening equation that they can come up with, like the Gaussian function, often simply referred to as a Gaussian. It's a function of this form, and this is not really the classical form of the Gaussian. This is, okay? And you look at that and you say g of x is equal to what, right? What is all that nonsense? Okay, but what's actually here is a scale factor. This number sigma changes. Really, g of x takes in x and sigma and a number over here called mu. But sigma is fixed in advance. And mu, that's called the average, or the, I think we'll just, yeah, mean. Mu and sigma are fixed. They're special values that change the shape of the Gaussian. And In reality, I'm bringing it up. A Gaussian function is just another simple piece of math. It's just a little bit more complicated than x squared because it produces a specific shape. That's the purpose of it, is to make a shape that is useful. All right, so right here, I copied this equation. A times E. E is another funny one, okay? E is a special magic number in mathematics. You learned it in calculus too, and it has special powers. Print math.e. It's 2.71828, etc. And it has special powers. There's all kinds of cool tricks that you can do with it that I will not get into. But the reason that it exists is because it can be used to do cool tricks. For example, making this Gaussian function, this curve, okay? And the purpose of the Gaussian function, all right, let's go back to the top. Here's A. I made it square root of 2 because I was fiddling with how big it was. B is the mean, the middle, where the top of the Gaussian function is. And C is how wide it is, how far it takes before it gets to the bottom over here. And a C of 1 makes it get to -2 before it hits the bottom. Okay, but then the function itself is just a number. It's A times E raised to the power of the stuff that was defined right here. X, that's the input value, right? It could be -1, it could be +1, it could be 0, minus B squared over 2 times C squared. And somebody just made this up. In fact, Carl Friedrich Gauss made it up a long time ago because it's a really useful shape for mathematicians. All right, so in your study of machine learning, you're going to see examples of this sort of thing. And what does it mean? It means a number. And all you have to do is decode all the different inputs that go into it in order to figure out what the number is. All right. The last part that I want to talk about today is called the derivative of a function. And the derivative for a function is cool. It's the subject of calculus. When you take calculus, the purpose of calculus is to learn the derivative. It's an amazing technology. It is a way of expressing rules of numbers that no one knew until Isaac Newton and a gentleman named Leibniz invented at about the same time. It did not, it was invented through careful writing on a piece of paper. And the purpose of it was to be able to say, how fast is a function changing? Okay, so a minute ago, I'll write derivative up here. The derivative of a function is the speed that the function is changing. And there are simple rules for calculating it, okay? So let's hop back to this. F of x equals x. All right, that's shaped like this, remember? And it goes up like that at exactly a speed of 1. All right. F of x equals x squared. That's that great U-shaped function, remember? It was like this. And f of x equals x cubed, which we saw a minute ago. I might need to bring it up again because I forget the shape. So like that. I'll bring it up again. Yeah. Okay. These functions have rates of change inside of them that you need to attend to. All right, so we write the derivative of a function like this, dy over dx. Okay, and there's a simple rule for converting them. You take any exponent of x, you move it down to be before it, and then you subtract 1 from the exponent that got moved down. All right, so let's see here. There's a 1 here. And so the 1 moves down in front of the x, and dy dx becomes, we subtract 1 from this now, so it becomes x to the 0, which is 1, becomes 1 times x raised to the 1 minus 1, which is equal to 1 times 1, which is equal to 1. All right, so the rate of change of this function is always this function, 1. It's going up by 1 all the time. 1, 1, 1, 1, 1, 1, 1, 1, 1. That's all it ever does. All right, we can do the same thing here. dy of dx equals, now we do the same thing. We pull the 2 down, 2 times x raised to the 2 minus 1. All right, so that's just equal to 2x. And when we graph this, that's cool. I will write that down, Abhinav. 2x simply becomes a faster line. But it is changing. All right, so now the thing that's interesting about this is that right now, 2x is negative. And you can see here it's decelerating. So it starts out and it's going down really, really fast. It's going down at a very high speed, a very large negative number. Like where this is 3, okay, this is 9, where this is minus 3. But the speed at which it is going down is minus 6. It's 2 times minus 3. So it's going down at minus 6. And it gradually decelerates towards 0. That's where it starts changing direction, okay? It flattens out here, which is very important. The 0 of the derivative of a function is the holy grail of machine learning. It is the thing that we're trying to get. It is why we write an algorithm, to try to solve a problem. Okay, and then it leaves 0 and it begins accelerating again. So when x is 1, the speed of its acceleration is 2. And when x is 2, the speed of its acceleration is 4. And there it goes, zip, pew, back up to the skies. And Abhinav wrote down great function. This is the derivative. This is the function for the derivative of f of x. And he writes it here. F of x to the n equals n times x raised to the n minus 1. All right. I shouldn't have written that there, actually. Let me see if I can do some GIMP magic. Grab this one. It's not going to work because of layers. GIMP always messes me up with layers. Move it. See, it's not what I want. Forget it. We'll just write the derivative down here on a different spot. All right, so we do the same thing. F of x equals x cubed. Its derivative. Uh-oh. Now I have something selected. I have to go up here, go to select, none. All right, back in business. dy of dx equals 3x squared. All right, so the derivative of this function is just x squared. It's precisely x squared, except it's even faster. Pew! Whoop! Straight up again. I like my sound effect. Let me pew, whoop. Nice. All right, and you can see this here because it's going up really, really fast right here. And then it slows down, gradually tracks across 0, and then it goes up really fast again. So there are hidden functions in every piece of data. Let me double check my to-dos to make sure I'm not going to miss anything. Yep, I think we're perfectly on time. I hope you're still paying attention, because this little bit here in the last 16 minutes is really why the preceding 44 minutes of conversation have happened. Now, if you already know all this stuff, great. You know, you're well positioned to mathematically understand the algorithms of machine learning. If you don't already know this stuff, maybe you feel like it's kind of fast, or maybe you feel like you're not getting it, just be glad that you didn't have to do 6 years of academic calculus to get this far, which many people did. There was something that I really wanted to say. This f of x, this y equals f of x, and this derivative of f of x is truly the basics of all mathematics. It's the most useful thing for you to know to be able to do math that's beyond arithmetic for, bookkeeping and for buying groceries and so on. The only kind of math that is simpler is algebra, the stuff that you studied probably in grade school. And algebra is actually much, 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 much harder than what we're talking about here. Algebra is something, being good at algebra and being good at calculus so that all of these things are intuitively obvious to you. There's only 2 ways to get it, okay? You can be 175 IQ super genius who intuitively captures every function that's shown to you, or you can do it a lot. You can just do lots and lots of math. And I know for me, when I was a student in school, I had ADHD and I was lazy and I didn't like my teachers and I didn't like my peers, and I wasn't going to sit there and do all that math homework. I just thought it was lame and irritating. I'd rather be playing video games. Okay, and it wasn't until I was much older that I could sit down and do the math. And it turns out that's the only way to learn, is by doing it over and over and over again. All right, so I'm finished with that little diatribe. I want to draw you some imaginary pictures of functions, but we don't know what the function is, because this is really what happens when you are doing machine learning. You get some numbers in that you didn't pick. Someone captured them from a sensor device or from a big machine learning database. And you draw them out, and this graph is just a catastrophe. But I'm gonna go with it. All right, 3, 1. There's a number here, and there's a 5 minus 1, right? And there's a 4, 4 here, and there's a 6 minus 4 here. Okay, this is what we really know about, for example, the pictures that make up cats and dogs. Okay, we've got some data. Well, there's one more value that we would have in this. That would be whether it was a cat or a dog, which I'm not going to dive into at the moment. Okay, but nobody told us what f of x is. Nobody knows what f of x is. And it gets harder and harder the more data there is and the more complicated analysis that you want. So f of x is not known. But maybe what we know is that this is a cat, and this is a dog, and this is a cat, and this is a dog. All right. And what we're going to try to do is we're going to try to make some predictions. We're going to feed these numbers into a machine. We'll call this V. But we could very well call it X or W or lambda or anything else that we wanted to. Okay, so we calculate this thing f of V. And this is a machine learning model that we invented. And the model on this pass, using the initial configuration, produces cat, 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 dog. All right. And so we say, let's say that cat minus cat is a 0, cat minus dog is a 1, cat minus cat is a 0, and dog minus dog is a 0. All right, so we only have one missed classification here. So what we do is we say that there's some function that we're trying to solve, f of x, that we don't know. But what we do know is when we put in all these values, the output of f of x is equal to 1. And we'll get into this in more detail in the course. But what we wanted it to be was 0. And so what we say is that the derivative at this point of f of x was equal to 1 minus 0. And we know that our function is off by some amount. And so we tweak the parameters. We push them back inside of here. We tweak the parameters by this number 1 that we learned about the derivative of the function. And we're able to then make another pass with the new parameters and see if things come out differently. What I'm trying to get to here is somewhere in the shape of the function, imagine that the shape of the error function is x squared, the one that we're just calculating. And right here, this is where we landed. We got a 1. dy of dx equals 1. Okay, but what we'd like for it to be is 0. And so we're going to continue adjusting our values to try to get that error, to try to get that derivative to move toward 1. And when it is equal to 0, when it is flat, that means we can't do any better. That means that if we go back this way, we're going to fall off of the best answer that we have. And if we go back this way, we're going to fall off the best answer that we have. And so the sole objective of building machine learning algorithms is essentially to figure out where dy dx equals 0. And that is the rate of change of our predictions. We put in numbers into an equation, and then we get out, for example, 1 is a bit too small, right? We get an error of 8. So we tweak the numbers, and then we get an error of 5. Or we tweak the numbers, and we get an error of 2, and we tweak the numbers, and we get down to 1. If we can get to a place where the error is 0, then we have essentially discovered the hidden function. We have discovered some function that maybe is like this. That describes which of this data is a cat and which of this data is a dog. Now, there's only one more piece of detail to give on this, which is that machine learning is harder than this, okay? Because most functions, the derivatives of most functions, hidden ones, the ones that we don't know, they have something called multiple optima. All right, so if this is f of x, then the derivative of this function is going to look kind of like this. It's hard to draw a derivative just from looking at it, but you can. Look how it's going up. Okay, that means its derivative is positive and highly positive. Okay, and as it goes over, it decelerates until it hits 0. See, because it started going negative again. Or yeah, it's starting going negative. It crosses negative. And here's where it switches back to positive again. It starts going positive. Am I going to draw the same one? Yeah. See, I told you it's a little tricky to do this. Positive, positive, positive. Crosses 0. Now it's negative. Now it crosses 0 again. Now it's positive. Now it crosses 0 and it's negative again, and it continues negative this way. So it looks kind of like this function. But the point is that the derivative is 0 here, and here, and here. And these spots all correspond with where the function changes direction. That is where our predictions start getting better, or where our predictions start getting worse again from whatever we're trying to get. And we don't know which of these is the real one. Some functions look like this. Some secret hidden functions that nobody knows look like this. And what a neural network does is it samples them all at the same time. It says, what about this one, and this one, and this one, and this one, and this one? Which one is the best? And it tweaks them all a little bit. And maybe it changes to go to this one, and to this one, and to this one, and it makes another attempt, and it tweaks them all a bit. And eventually it finds maybe the best one, which is here, which we only know based on the error that we've calculated. So I hope that this last part has made sense to you. It's really fun to talk about, and I think it's going to need another lesson. But this is the essence of calculating derivatives for the purpose of solving unknown equations, which is the goal of machine learning. And the purpose of every machine that we build, neural nets, support vector machines, random forests, and everything else. This is the basis of the study. Any questions? I'm just reading through the chat logs looking for questions. Okay. So Muhan asks, how do I conceptualize how a function can describe a cat? What am I missing? And it's tricky to draw a picture of because it's binary data, but essentially what you have is something like this. And this is two-dimensional data, so we'll take it down to make it even more obvious. 3, 2, -1, -4. And then if it's a cat, it's a 0. And if it's a dog, it's a 1. So here's a -4. Here's a -1. And there's a graph here that kind of follows this like this over to 2 and 3. Here's the 2, and here's the 3. Okay, so the function says if it's a -4 or a -1, it's a dog. And if it's a 2 or a 3, it's a cat because it has a value of 1. And so our equation, our machine learning algorithm is supposed to figure out exactly which value for this simple input to divide at, to decide any number that's less than this is a dog, and anything that's greater than this is a cat. But this is the simplest possible example with only two-dimensional data. It's got one-dimensional input, and it's got a second dimension for just the classification. And in reality, we've got, potentially dozens or hundreds of thousands of dimensions. Sean, I'm not sure what your question means. James says, will machine learning math dive any further than the functions I presented? There will be the full calculation of backpropagation of neural networks as part of our math study. And as we build certain models, we will go through the math that defines the relationships of numbers in those models. But the fundamental concept of math that you need to know is this function optimization goal. Someone asks, why do you want to find the derivative is equal to 0? And there's some good answers here. It's where the function has a minimum or a maximum. And Marina, depending on the shape of your equation, it could be a minimum or a maximum. If we're trying to minimize error, absolutely, we want the minimum. Abhinav, how to find a function based on data. So the simplest way of doing it is using a tool called linear regression, which we will learn in the main coursework. Regression tells you the function for a set of data, but it's not very smart, and it doesn't work as well as the data gets more complicated. Marina, thanks for your good answers in Slack. They're good descriptions. I think that we're good to go. Any more questions tonight? Here, I should pop this down here. All right, everybody, it's 6:59. What we talked about today gives you preparation to do the first half of the ML pre-coursework, which actually was public. So many of you went out and did some forensics in the repository to find this, the ML pre-course repository. The first half of this involves unit tests about taking the derivatives of functions just to exercise your Python and to exercise your most simple calculus brain. Tomorrow, we're going to do linear algebra, which is almost exactly the same as what we've done here, except it's the idea of taking individual values, 1 point, and moving it around and calculating its relationship to other points. And that's the next most important part of the mathematics of machine learning. Finally, remember to sign up for the Lambda School Artificial Intelligence course. I'm going to paste the link into YouTube one more time because I believe that all of you who are in Slack already have that. So Kelvin asked, do you need to write a function that computes the derivative? No. Simply figure out what the derivative is with pen and paper and write a function that returns that. Writing a function that computes the derivative is much more challenging and not as left as an exercise for the reader, as an academic would say. Maximimia, indeed. Thanks, everybody. Thanks for your wisdom and your contributions, and I look forward to seeing you tomorrow.